Every year, lots of university students will participate in AI-AADBF competition in the United States. Students can use their engineering concepts, innovations to design the aircraft. This year, HKUST also sent a team for a competition. For every year, the design standard will be different. We have to follow the rules to design the aircraft. Apart from rules, the scoring of the competition is also different every year. Therefore, before joining in the event, we have to know the winning requirement first. Basically, if you have an interest, you can check all the material on the AIAADBF website. For this year, we have produced an aircraft to the competition which held on the 2000 in United States. And now, you may ask why the design of the aircraft like this. Now, let us to make an interview to this year's Chief Design Engineer to know what is going on about this year's design.
First of all, this one is a final prototype that we bought here in the US. But before this one, we have a few other prototypes. Starting from the very first beginning, we have two footplanes, one with a conventional tailway and one with a T-tailway. But finally, we chose conventional tailway because the T-tail is not as stable as this one, and it's hard to manufacture. And then shoot us at 90 degrees between the horizontal and vertical stabilizer. So then we chose the conventional one. And then actually, starting from the first winner plane to the final winner plane, the configuration is more or less the same. What's different is we drill some more holes in the tailway, so we save more weight, user weight. And then we changed the airfoil from capacities to AirCap 0015 because this one is having less drag. So this is how we bring this prototype up. Okay, so actually, the biggest concern for the tailway is we need to generate enough lift for the plane when it is hand launched, because the rule said that we have to hand launch during the competition. So we have to ensure the tailway size, for example, especially the horizontal stabilizer, I think is sufficient wing area, and then the elevator is large enough to give it momentum to let the plane pitch up when we hand launch this plane. So this is one of them. And then another rule is this year we have to fold the wings and fit it into the launch tube. So we have to make sure the horizontal stabilizer can flip up and then fit into the launch tube. And originally we want to save on the servo motors. You can see now there's two servo motors there. Actually, at the beginning we just want one and link up the two elevator. Maybe I should run it out. Oops. You see there's two servo motors here, one here, and one here. And then in order to reduce weight, we only want one at the beginning. And then link up this two. So then we can save another maybe 50 grams for a servo motor. But we found out that if we link up that, it's impossible to fold it. So we have to do it with two separate elevator and two separate servo motors. So this is one of the limitations because of the rules. And then this year we have a connection box, which is the first time AIG did it. Usually they just do the tailwing with airfoil from one side to the other side. And this connection box, I won't say it's very hard to manufacture it, but it has to be very concise when you manufacture it. Otherwise, you will break your twisting, and then the whole thing will be twisted. And then we have to also ensure there's enough space for the servo cables to pass through. Otherwise, they cannot come up from this hole. Yeah, this is some limitation because of the rules. actually we first set to the dimension for a main wing, and then we calculate the size of the tail wing according to some standard formulas and the factors, the ratio between the main wing and the stabilizers, and the factor is various. It is just a reference to us because in reality the plane having different ratio between the main wing and the tail wing. So we first assume a factor and calculate the size of the tail wing and put it into our analysis and see whether it's stable enough, whether it can achieve our goal, our target, and then we finally test it in test flight. And we receive command from the pilot to see whether the size of the tail wing is sufficient for the pilot to control the whole aircraft.
So the ratios you mentioned are some ratios that you just find from the internet or some reference to the textbooks or what?
We find it from the website. In reality, for commercial plane, fight aircraft, they have a ratio between main wing and the stabilizers. We do the calculation according to this kind of plane. We also take reference from glider because we hope that because glider is having a lot of high lift coefficient. So this is one of the approach throughout this few months because we want to have technology that ensures the lift is high enough.
So is it a similar approach for how you guys find the airfoil for the tail part?
Actually, for the airfoil is pretty standard. There's not a lot of choices, but we maintain the airfoil shape in symmetric. So we don't want to produce extra lift and make the aircraft performance to be stable.
Okay.
First of all, for the tail wing, the final aircraft is having a benefit in its weight because the landing part is much lighter than the previous one. There's only 2 wires here. The previous one, I think, is at least a few times more heavier than this one.
Because you have a wheel?
No. We are not having a wheel here. There's a wire, 2 wires here.
But for the previous design?
Previous one, we have some wooden layer, triangular wooden layer, and then we put a carbon rod here. So when it lands, the carbon rod will hit on the ground. So it was replaced by these 2 wires. And then for maybe another benefit is this triangular empty slot. Originally we don't have it, so sometimes when this tilt to a side and this tilt up, it will block each other. And after we built this empty slot, we solved this problem. So this is another precise design. And then for maybe one more advantage is this one. This for the we have a extra tube part here because when we do the drop test, which is inside the launch tube, this is the tube which can support the impact force instead of the stabilizers, so we won't hurt this. We won't hurt that. Maybe for disadvantage, actually I would say this is we don't have much disadvantage for this one. but if you push me to say some, I would say we should have less servo motors. We should find a way to link up this tube so that we can save some more weight. And another possible improvement is this clip. Because we cannot use our hand to clip off this tube, and when clicking on this is not a problem. When we have to detach it, we have to use tools to detach the clip here. We cannot use our hand because there's no space for our finger to just get into the hole and clip it. So this is another possible modification if we have to modify it again. Because of this year's rules, we have to fold it. So there's a wing fold mechanism here, which is unique in this ear. And inside the wing fold mechanism, we have some universal joints, and then we have some support, counter support, to make sure it can fold in the right direction. So this is some point that is special for this ear.
So, do you mean that the tail part can also fold? Or just...
Yeah, it can fold.
Oh, okay.
It can fold. The tail can fold 90 degrees from like this to here. So that's three stabilizer can be in parallel with each other, and simultaneously the main wing is also fold and fold in this way, so there's enough space for the main wing.
Okay.
I think you mean there's some another shape of tails.
Yeah, maybe
There's some
not only shape,
tail.
but would you do any modification on the tail part after this completion?
I think for the sizing, I won't change a lot for the sizing, but I will choose another material instead of wood. And because during the competition, I saw some cases using some one piece layer. They use just use a layer for a tail. You don't have any airfoil shape. They do not use any wood. So maybe we can just use a piece of layer instead of this one. I think the benefits why they are using this because it's reduce more weight and it's much easier to manufacture. We don't have to go through laser cutting, sanding work. They just have to assemble the three layers, so it's easier.
So you think maybe in the next year they can pay more attention in the weight instead of the aerodynamic performance?
Yeah, sure, because RAC is really important. If you get a smaller RAC, the result and the scores is much higher. It's significantly higher. The RAC is very important. I think the quality control is very important. There should not be any twisting, and each airfoil should be parallel to each other, and yeah, otherwise, aerodynamic performance is very sensitive. Any minor defect will affect the performance, so we have to be very precise. Yeah. And also for the main wing and those interesting.
So, thank you for...
Okay, thank you. Okay, thank you.
Thank you.
Thank you.
Perfect.
Actually, we can use the XFLR analysis software to demonstrate the performance of the aircraft. Therefore, it can let us to know whether the design possible is or not. And now let us to know briefly how to use it.
So this is the XFLR analysis. First of all, we have to settle the dimension and the sizing of the main wing and the tail wing. We can amend the sizing using the active function, which pop a new window, and we have already defined the airfoil for the main wing, the dimension of it, and there's a internal twist there. So according to the main wing, we do calculation of the sizing of the tail wing. First of all, we have to define the position of the tail wing. We input the position here in this empty boxes, and then we go to the elevator. We choose the airfoil that we are using. There's no twist, and the chord length and the length of the horizontal stabilizer. And the same for the fin. We choose all this dimensioning for the fin, and afterwards we confirm the dimensioning of them, and then we go for an analysis which we want to see the result of how the aircraft perform. So we go to define analysis. In this analysis, we want to have a fixed lift, and then we choose our VLM1 as the analysis method. And this is some other parameters that you can change. Okay, so after when you have this defined the analysis, you can go to perform an analysis. But before that, we want to see the performance of the aircraft at different angle of attack. So we say we want to see the angle of attack from -2 degrees to 15 degrees, and we are recording data in every 0.5 degree. And we go for an analysis. In this result box, you can choose which kind of information that you want, like the lift and induced drag, and also the moment. And at the right bottom corner of this black window, you can see some performance of the aircraft. So like when we are having 0 angle of attack, the speed will be 20.51 meters per second, and there's some other information like efficiency and lift to drag ratio, and at the bottom left corner you can see some calculation of the sizing of it, like the wingspan, wing area, etc. So this is how we conduct the XFL R5 analysis.